Excellent. All right. Welcome, everyone. Thanks for joining us for this guest lecture by Donghun Kim. I'm happy that he could make it today. We're right on track with talking about MPC in class as well. About Donghun, he received his Ph.D. from Purdue. He focused on thermal energy system modeling, design and control. He served as a research assistant professor at the School of Mechanical Engineering at Purdue, and currently holds a position of computational research scientist at Lawrence Berkeley National Lab. His academic background and interests encompass modeling, system identification, machine learning, controls, and optimization, aimed for developing, evaluating, and deploying advanced building HVAC control algorithms. All the good stuff. And he also is the subcommittee chair for building operation and dynamics, the TC 7.5 for ASHRAE. So at the heart of practical application. So Donghun, very pleased to have you here. Please take it away. The floor is yours.
Yeah, thank you. It's good morning still in there.
It's good.
Yeah.
Good morning.
Good morning, everyone. Okay. I wanted to talk about, I think what most of you are interested in or studying in the field of advanced controls in building sectors. I wanted to start touching some weakness point of advanced controls applied to the building. This is my argument, but based on my knowledge, I think, 0.00001% of a building currently employed advanced control, despite the enormous amount of research. When I say advanced control, it's more about data-driven, optimal control rather than human-based, rule-based control. Let me talk about some like the data. I searched Scopus yesterday, actually, and try to identify how many papers are published and tracked in Scopus with the keyword of model predictive controls and buildings. It only includes the model predictive control. It's not including, others. But as you can see, there's like around 5,000 papers are available until by yesterday, and the number of paper increases dramatically. There's like 600 papers last year published in a good journal. It's starting from 1990s. One of the very pioneering paper is I showed in there. MPC has been applied to building for about 3 decades, for more than 3 decades, and still it's very difficult to see the building that adopts advanced controls. And when I add additional terms like demonstration or field test in addition to model predictive control and buildings, you can see the number of a paper goes down to below 10s every year. In terms of a percentage, it's less than 2%, but this 2% is still exaggerated because this is a literature, so that scientists working really hard for the demonstration. But in reality, compared to the tens of millions of buildings in the United States, considering the reality, that number 0.0001% is the number that I come up with. This is a huge problem, especially today. This seminar that I wanted to talk about is, first, why this is happening. What's the gap? What's the challenges of bringing these fancy advanced technologies to the real building market? And the second, how to resolve this problem. And why resolving this problem is important. So I wanted to talk about those perspectives rather than showing some mathematical equations. I wanted to emphasize this in this seminar. Okay. So why is the wide adoption of advanced control in real building market is really urgent? There are a couple of points over there. Nowadays, buildings get more and more complicated. It includes renewable energy, solar PVs, and summer energy storage, potentially, and the electrochemical batteries that may include EV charging station as well. Building owners or facility operators are very struggling, saying that they have PVs, batteries, and summer energy storages, but an HVAC system, but they don't know how to control. It's a current problem they are facing. And another problem, maybe more important. I think you are familiar with duct curve. And duct curve really shows how does the net demand from the grid perspective, what is the electrical load that they have to meet at each instant of time. As the renewable, by the way, can you see my movement of mouse point?
Yeah, we can see the mouse.
Good. As the PV solar generation, renewable energy is penetrated to the grid and behind the meter, you can see the loads become lower and lower and lower when when the sun is available. But when sun is gone, then we can see the immediate, very rapid increase of electrical demand. Because originally at the time, it looks like a duck. Here's the duck belly and duck neck and head. So we said it's a duck curve. But nowadays, it's getting deeper and deeper. Now it's like 2024. It's more deeper. It's no longer a duck. It's more like a giraffe with a very long neck. There's a huge problem of this. First, like here, our load when the renewable is peaks, load is very small. So the utilities may touch the nuclear power plant. That's not going to happen because it caused a huge unstable problem in nuclear power operation. So what they are currently doing is they just waste the renewable energies. They just curtail the renewable energies. In California, tens of gigawatt of hour of renewable energies has been over-generated. It's just used uselessly. It's just wasted. And another problem is in the slope of the neck. As this slope increases very rapidly, we don't want it to move away from a gas turbine power plant because of this speed. It's hard to meet this, hard to follow this speed with other power generation plant. Because of this, like we are struggling to adopt more clean energies because we already overgenerate renewable energies, and also we cannot move away from the gas turbines or something. So there's a huge problem and how to resolve these issues. The only possible way is just putting some huge giant batteries and shift the load so that store some energies when the renewable is overgenerated and then use that during when the sun is gone. But electrochemical battery is expensive. We need to find out more economic way of doing this. That's where the importance of advanced control in building comes. I'm talking about some of the California policies. California's decided they wanted to meet 7 gigawatt load shifting goals using a flexible load, using the load flexibility. Load flexibility is like a kind of a virtual power generator that could absorb or like spend more depending on the needs of the grid. So it acts just like a building load side acts just like a virtual batteries. So California set these huge goals in by 2030. We only have like 5 to 6 years left, and they wanted to meet 7 gigawatt level of load shifting, only using the load flexibility. And buildings, because the building typically consumes 70% of electrical energies in the United States, the role of building is very important. So that's the problem. We need to solve this problem. We need to bring the fancy advanced technologies to the real building market now. So, but as I mentioned in a previous slide, we are not that stage yet. So how to resolve this problem, considering this urgent matter? It's obvious. Just try to do some extensive demonstration, show the compelling savings so that the industry can see the benefit or the the dollar savings they can adopt and bring the technologies to the real market. And we have to show the proved scalability and continue working, commercializing those kind of technologies across the various buildings of HVAC system. Building is not just simple, it has a variety of HVAC system, has showing some different characteristics. And also moving beyond the algorithm development. Algorithm development is an important piece, but considering this moment, we have to put enormous effort on the demonstration, commercialization, showing some compelling savings. Okay, I have, in order to address this problem, I and my colleagues at Lawrence Berkeley National Lab have been really work hard for demonstrating some advanced technologies, including model predictive controls for multiple sites and the reinforcement learning as well. And some of the sites that we have been demonstrated advanced control is showing here. It's just a sample. It doesn't cover everything, but it has a kind of laboratory settings and church, small retail stores like restaurants and a convenience store, K-12 schools, small offices, large offices, and campuses like district energy system. I wanted to kind of talk about 2 main sectors. One is small and medium-sized commercial building, and the other one is a large commercial and the campus level studies, because they have its own opportunities, technical and non-technical challenges. So let me talk about the small and medium-sized commercial building here. The opportunities and challenges. Small and medium-sized commercial building, here I'm mainly talking about is consider like a buildings that is served by multiple rooftop unit, package unit. This is one example. See, here's the building, and you can see the 4 rooftop unit over there. This one, the below is another example with buildings served by 1 RTUs or 2 to 3 RTUs package unit and those kind of things. You can see this type of buildings everywhere in the United States, including, even like McDonald's restaurants and like Walmart, Home Depots, like everywhere, factories. The opportunity for the small and medium-sized commercial building, it is a tremendous demand response resources. It consumes around 50% of energy spent in the entire big commercial building sector. So it's a big player. And in terms of floor area, that represent a summer mass or summer mass associated with the building, it has like a 50% of total floor area of the entire commercial building sectors as well. So it has a huge demand response resources. And another important opportunity is, so majority of small and medium-sized commercial building, as I described, it has very consistent HVAC system configuration. That means served by multiple rooftop unit, and each rooftop unit has its own thermostat. That system structure doesn't change. It's like, although the number of RTUs and the type of RTU, performance RTU could be different, but in terms of this setup is not changing. It's good because that means from the controller perspective, control engineering perspective, the control input is fixed and the control output is fixed because of the consistency, right? Control input here could be the set point of the thermostat, and control output could be the temperature and the power usage. That doesn't change. And the underlying dynamic model between the input and output doesn't change, although the characteristic could be the different. So this one really gives a tremendous potential for us if we develop a advanced control that works for one building that could be applied to another, tens of thousands of a building because of the consistency of input and output and the underlying dynamics between those input and outputs. Challenges. Lack of sensor, they don't have installed medicine. We don't know what's the supply temperature and return air temperature, and we don't know what's the airflow rate, and even like we don't know what's the power internal heat gain. No such a sensor. And this continuous and nonlinear nature of the controllable input, that's like, although our set point control is continuous, but thermostat itself is crazy. Has internal, hysteresis controls thermostat, and typically thermostat, the rooftop unit is a stages, is either on and off or one stage, two stage. That's it. It's not continuous variable. So there's some challenges, but more importantly, economics. People doesn't want to spend a lot of money in a year. They are only paying like $1,000 per month, although we argue that we can save 20% of your utility bills, then including some of the service fees and installation cost. Typically, because the payback period goes above 4 years. So that doesn't make sense for the building owners, especially for small and medium-sized commercial building. So in order to address these problems, we have to develop a very low-cost model predictive control. It doesn't need to be show very optimal one, but at least to do some automatic demand response and some savings. My research has been focused on previously developing such a low-cost model predictive controls, and the left-hand side shows the how does the MPC work, the control architecture, It's like a 2016. We used the Wi-Fi web-enabled thermostat, and every time sampling time, we collect the data of the thermostat, and by communicating to the thermostat server database, and collect all the information of this building and that building across the United States, and for each individual building, we solve optimal control problem, model predictive control problem, and determine what's the set point for each thermostat and send that decision to the thermostat. So that was the control architecture, and as you can see, database is already there, and that's what thermostat provider is providing to us. And the web-enabled thermostat, that's the cost, but nowadays, it's like $150 around per each thermostat. So retrofitting with this, web-enabled thermostat is not a big burden. And other than that, other than this cost, there's no like special devices included in here. So you can imagine it's very low cost. We are not adding additional sensors. Very low cost, just fully leverage the thermostat existing infrastructure and solve the model predictive control. There's two references I add that if you are interested in looking at what's the mathematical formulations and what's the challenges, and please look at this. But one thing that I wanted to emphasize is the focus of this model predictive control is there are two main objectives. One is demand reduction. We wanted to regulate or reduce the peak power. That's the version one. And the second one is we wanted to add optimal load shifting in response to the dynamic price signal. That's the version 2. There's a 2 version has been developed. Main feature, again, so low cost and scalability. This one is the point is where the old MPC has been demonstrated in 2016. That's about 8 years ago. And I have done this demonstration just within just deployment and modeling and implementation within a month, working with commercial partners. That shows the scalability. It's already proved, and the version 1 has been commercialized in the next year after this activity. So what about some real field performance of this MPC that I wanted to share? One thing is, first, demand reduction capability. This one is not the result. This left-hand figure shows that what's the current problem associated with multiple RTUs. And this is joint air temperature, and there's a full rooftop unit. And you can see during a summer, the temperature goes very high. And once the occupied period starts due to the termination of a night setup, the set point lower and temperature reduced very dramatically. But because of this nice setup, we believe is much more energy efficient. It kicks in, all the RTU has to run with their full speed and shows the peak power. This is only 4 RTUs, but imagine buildings have a 30 number of RTUs, and this peak is huge. And also, there's unnecessary peak as well, because that's is just like coincidentally happening where because of the decentralized control nature of the current thermostat-based control, we cannot prevent this problem. We developed the MPC to using that architecture, control architecture, and shows the benefit. And the red line is when the conventional control, set-point control has been implemented. And this is when the UC on model predictive control is turning on and turning off, and keep repeating this process to show the benefit. And you can see just compare this peak between those two controls. The temperature maintains temperature and the humidity maintains pretty in a consistent level, but the power behavior is totally different. So we have shown that this peak is really unnecessary, and we can reduce the peak demand. And that's the kind of field test, the result associated with the demand savings and number of RTUs and site locations. And consistently, like 20 to 30%, we can regulate the peak. But this is version 1. We have to show that the performance of the load shifting, which is the needs of the current utility. And the version 2 demonstration has done, the first one shows the temperature. There's a 2 package unit in this building, and that shows the power, instantaneous power for each unit, unit 1 and unit 2. The size is different, so the power scale is, the power magnitude is different, and this is just a summation. And the shaded area is where the where the electric price is high. On-peak to off ratio is a 2 in this case. Again, red one is conventional, blue one is when the MPC is on and keep repeating daily and daily. And you can see the temperature profiles as opposed to the conventional one. Before electric price jump, where this is the shaded area, electric price is high. Before this happens, model predictive control try to pre-cool the space within the comfort bound that has been specified by user. And you can see the pre-cooling effort in order to store the energy using the summer mass of the building and then reduce the peak or the energy consumed during the on-peak price period. One important thing is the peak, right? Even though MPC provide pre-cooling, there's no like the previous problem happenings, and it is very well coordinated. We repeated this one over like a couple of months and collect conventional data profile associated with the total power and perform the moving average because it's just like on and off, it's hard to analyze. We apply the moving average for each day of power profile and just showing the result in aggregated way for the conventional and model predictive control. And these two, the below one is to really compare the representative profile between the MPC, which is blue, and the conventional control, and the on-peak price period. And you can see the model predictive control try to charge the summer mass of the building before electric price jump and utilize that energy when the electric price is high. We have to make sure that the temperature, it doesn't affect the temperature significantly. This small figure compares the same, the temperature range and the model predictive control. And this seen line shows the lower bound that has been imposed to the MPC by the user. It missed the lower bound and just to do the right thing. Next one is another interesting activities MPC has been developed for dual fuel heat pump system. Dual fuel means it's a heat pump, but with gas furnaces, because market building owners doesn't want to remove their existing gas furnaces. They wanted to leave it as a backup heater, just in case. It's a market. The dual fuel heat pump system is very consistent, and because of that, we wanted to build a model predictive control and do the same thing. I wanted to talk about. I don't want to talk about all the details, but that there's like 5 heat pumps and 1 gas furnaces. And we did the same comparison, running the MPC one day and the other day conventional controls, and keep repeating this process and evaluate what's the savings. Let me emphasize the cost reductions compared to the baseline of the MPC. There's some cost reduction, and more importantly, MPC is able to get rid of all the gas usages during the experimental period. That's important because that's the goal of installing a heat pump. The savings is summarized in there. It's pretty visible. And again, it's like the most exciting thing is it is able to completely eliminate the gas use. So there's a unnecessary use of gas associated with the conventional control, and the advanced control can remove. It shows really the potentials of the advanced control. Scalability, that has been proved, as I mentioned, even like in 2016, I've shown, and now I'm working with commercial partners that deploys these controls to over currently around like 200 buildings is installed. The MPC has been installed, and the location it shows is expanding the market. Okay. So far, I talk about some of the challenges and opportunities small and medium commercial building, but now let me briefly talk about, within 10 minutes, talk about a large commercial building and district energy system, what's the opportunities and challenges, and then some real performance, field performance, and I'd like to open up questions. Opportunities. Oops, I need to update this figure. Sorry about that, but please ignore this. For large and large commercial and district energy system, the most biggest opportunity is, I think, is a greater effectiveness in terms of dollar savings potential per building or district energy system, in terms of load shifting capacity per building. This is like incomparable to a small, medium commercial building. For example, let's say for a large district energy system. District energy system, by the way, means it's like a summer plant, or sometimes it include the electrical plant. That plant provide heating and cooling and electricities potentially to multiple buildings, but essentially it's a summer electric energy system. Or sometimes we can just say summer energy system if that is cooling plant or the heating plant. If we develop a advanced control and assuming that it is working correct, then the savings potential, only single deployment for this type of system is we can show the megawatt scale of load shifting, just only single deployment. And the save is $10,000 per month. So this is the number that I actually extracted for working with the real demonstration partners per month. There's a huge potential. So small and medium-sized commercial buildings, we can save $100 per month, but here, tens of thousands of dollars. So there's a huge potential and attractive things associated with large commercial and district energy system. But challenges, I listed here bunch of challenges. I don't want to read through everything, but if you have questions, I'm happy to answer it during a Q&A section. I put all the challenges related to this in this reference. So if you're interested in, also have a look. Some quick summary of the demonstration activities and real performance. We have developed a model predictive control for district cooling system at the University of California, Merced. It has 5,000 refrigerant ton chillers. There's 5 chillers, and the total capacity is around 5,000 ton. And this silver tank shows the chilled water tank. Is just a huge tank filled with chilled water. Basically, the summer energy storage is it can store 2 million gallons of water, and it has a 5 megawatt scale solar farm is there, and it serves around 40 buildings. 40, I think, is getting more from the last year. So we developed and tested the MPC with the plant, and and tested 2 different things. One is we injected a typical dynamic utility price signal to the building and see what's the savings, and dollar savings especially associated with that, the MPC. And another one is we took a carbon price signal from from the grid, and saying that at this time of moment, some metric ton of CO2 equivalent is generated per each each kilowatt uses. We are taking this signal that indicates whether the grid is dirty or clean, and see how does the MPC behaves for this building. Left-hand side shows the conventional, the dollar per kilowatt hour using that signal, and let the MPC runs, and this is the result. This area is 4 to 9, where the price is high, and the chiller plant power, you can see the multiple days it try to not to use his chiller plant because the electric price is high. And this one, the second one shows the state of charge. Basically, the chilled water height within a chiller, and it shows that chilled water level is reduced. That means chilled water is utilized because we are not running a chiller, but we have to meet cooling load of the campus. And the last one shows the campus net power. I haven't mentioned that, but one important thing is we'd like to incentivize the self-consumption of on-site 5 megawatt renewables. So that's also included in the MPC formulation. Campus net power is positive. That means like there's no power flows from the campus to the grid. If that happens, then it must show a negative value. But here, but previously we saw the down to -2 megawatt scale power flows into the grid, but after running the MPC, we eliminated this problem as well, and also the shifting capabilities. And right-hand side is getting a signal from the CO2, and compare the result after running multiple days of MPCs. The red one, like before, the conventional blue one is model predictive control, and the y-axis is campus net power consumption. Again, positive means the campus is using the energy or the power. The negative means the power is being flowed into the grid from the campus. The red one, you can see the negative, as I mentioned, like a -2 megawatt scale. Average daily profile is not just the instance of the day, it's multiple days and representative profile. And typically it results in -2. The 2 megawatt flows into the grid, but we totally eliminate this problem after running the MPC, and we smooth this kind of the duck curve. We eventually very effectively show this. And this is self-consumption improvement and the associated with the carbon savings and the peak demand reduction. For the carbon savings, just to clarify that there's no carbon uses associated with the chiller plant because it's all the electrical chiller and a cooling tower pump. There's no direct gas usages unless the heating plant. But the use of power is that has to meet by the grid, and grid have to use some of the gas component to meet the load. And that's the savings that we are achieving. We are not directly saving the campus level carbon uses, but savings the grid level based on the signal. And every day I calculated what's the savings per day, CO2 savings per day, using running the MPC. And that is equivalent of driving the car from the Berkeley to the New York or the Washington DC driving. That's the emission is we are eliminating just 1 day of this CO2 consumptions. Summary, lesson learned, I wanted to share. There's enormous unexpected problems in real buildings that like how to be captured in the simulations. Some very important keys that I think many people could ignore is do not assume that we have all sensors available. Like there are like a small and medium cycle, we don't have any sensors other than a thermostat. That's it, and we are not able to install it not because of technical reason, because of economic reasons. And a major disturbance is buildings never be white noise Gaussian process. That's a typical assumption in a system ID or the conventional stochastic MPC, the development is not true. And do not assume that everything is controllable. That's a big mistake. It's like, it's not because of technical reason. We can do that, but the effort to make it is tremendous. So it's very difficult to change it. We have to follow, it is what it is. And one thing, one critical piece, very important, is if your control of input changes, your underlying dynamics from input to output map will change. That means we may have to regenerate, reformulate the MPC, or retuning the reinforcement learning if it's the machine learning technique. So it's a huge problem I wanted to share. So my final conclusion is basically repeat what I've said, but it's like real world performance penetration of advanced control is really essential for decarbonizing the grid and maximize clean energy use. Thank you so much.
Thank you, Donghun. Very nice presentation. Any questions from the audience here or online? Feel free to post in the chat, and I'll kick it off because I have a lot, probably too many, so we'll have to talk again, Donghun. But one technical question that I was curious in the beginning when you talked about the thermostats.
Yep.
How do you deal with the modeling part of the MPC when everything's in the cloud and you only get the thermostat readings?
That's a big part that I have been struggled. So I can say because of the large unmeasured disturbances, we don't know what's going on. Whether the people open the doors, like windows, that change the dynamics of a building HVAC system and everything. So the performance of the model is I can say not very accurate. That's the limitation because of sensor. It's not because of the system IDs or the algorithm limitation. It's because of sensor limitation. It's impossible to model just using very limited sensors to capturing everything. It's mathematically impossible. I think I can prove it. So. But one way that I have been figuring out is there is some way of developing a better model. Better means better, like it captures more realistic behavior and reflect some, capturing some dynamics, although it's not perfect, some dynamics, especially like related to some indication of a summer mass R value and C values is still so. And in terms of technologies, multiple technologies, one is I end up with choosing a gray box model in order to make sure that the energy heat balance is preserved and stability to preserve the stability, because the lack of limited sensors, bunch of the algorithms could result in unstable dynamic model.
Mhm.
So in order to preserve the stability, I end up with stability and preserving some energy balances and physical meaning. I end up with choosing a gray box model. And then I develop a somewhat special system identification algorithm that try to model or measure disturbances in the system ID level, algorithm level, try to model, not just modeling the system part, the true system part, input and output. It also try to model the unmeasured disturbances, and try to compensate this problem. And also, the important thing is the experiment of design, how to generate a good data. That's also the key. So it's like a multiple combination of the technologies.
Cool, thank you. Yeah, Yuan posed a question in the chat. He asked, is there a case or potential issue with the long-term testing period, summer or 1 year, summer and winter for MPC? Or are you limited to single seasons only?
That's a good question. Currently, the longest site that has been implemented continuously MPC is one school, and that MPC is continuously running over a year at this moment. The other buildings, I don't know, because again, like as I mentioned at the beginning, one company has been commercialized. So they are working with lots of customers, and I don't have the vision in their business activities. Yeah, another buildings that is not like a year season. That's mainly because I'm a researcher funded by the state government or some other sponsors. If the funding is limited, then for me there's no option to continue working on this. Yeah, so that's actually you raised a good point. To make this happen in real time continuously, we have to work with commercial partners who can take over the algorithm and work, because I think our role as a researcher, and all of you over there, right, is not just implementing one single stuff. We would like to identify the problem, improve the algorithm, like test it. So if that's the point, then in order to make it really the impact for a market, you have to work with commercial partners.
Right. Thank you. If there are other questions, put them in the chat, or any questions here. I don't want one question that bothers me sometimes, not sometimes, but I want to hear your opinion, sort of like the bigger picture, right? And I'll give you an anecdote about 15 years ago when I started working on this, because somebody who worked a lot on MPC in buildings before said, it's very complicated to make it happen in buildings, and as you showed, it is very complicated. But there's one way, which is if it's demanded by law, basically, kind of like in cars or something like that, right? So I wonder, and this is 15 years ago when emissions were not really, and peak demand and duck curve were not really where they are today,
Yeah,
right?
right.
So I wonder, in your view, and also as part of your ASHRAE, committee sort of, activities, do you see any shift in the legislation that might actually make your life a lot easier by making demands on the performance of the buildings that could only be achieved by implementing some advanced algorithms?
They are not like a specifying the, hey, use the MPC, otherwise, we'll give a penalty. They are not doing this, but this kind of thing here, I'm sharing slide, they give a huge, very challenging, the goals, 2 GW load shifting goals using the load flexibility. This kind of goal, I think, is really promotes for researchers and others to work really hard on implementing a optimal controls in a real building. Actually, because of these things and the transition from conventional previous fossil fuel based power plant to the renewables, that drives, just shown in here, a increased load flexibility. And actually market is shifting towards to a like increased need of the aggregator, electrical aggregator. And that's one thing. And the second thing is that there are many startups recently launched to sell model predictive controls, and although they are not saying model predictive control because customer doesn't understand what is the model, they always said AI. Whatever the underlying algorithm, they always say AI because that makes a customer attractive. There are several startups and even large companies are selling a model predictive control as a product. One company is that I mentioned, they already commercialized, but it's a small companies. But as far as I know, there are at least 10 small startup companies are selling the MPC as a product, and like 3 to 4 large, in national scale companies are selling a model predictive control. Very recently, within 5 years, that really reflects the actual changes in a market, and companies actually see the benefits, the dollar benefit in this area.
Yeah, that is very exciting to hear. A lot of opportunities for folks graduating these days.
Yeah.
All righty. Well, we're coming up. So is there any other question in the audience, perhaps? Or not? No? Well, Donghun, thank you again. I hope you can share the slides with us so we can make them available. And
Sure, I will. And yeah, one thing that I haven't mentioned is I'm hiring several postdoctoral researchers. So I will share my slide. If you are interested in that position, so please feel free to contact me.
Yeah, we'll make advertisement for you, definitely.
Great.
Thank you, Donghun. We enjoyed your presentation, and I hope you have a great day. Thank you.
Thank you so much for this exciting chance to present my work, and I hope to see you next time.
Thank you, Donghun. Take care.
Bye.
Thanks, everyone. Bye-bye.
Everyone, bye.